Ramanujan lecture on applied math perspectives on stochastic climate models.
Thank you. So, my next two lectures, since there are so many talks on tropical meteorology, my next two lectures are oriented toward what the future is for climate science from various perspectives. And there's a group of us, and I would say Tim Palmer from ECMWF and now Royal Society professor at Oxford, and myself are the two leading advocates of the future for climate models. And they will be stochastic models, not deterministic models. And I will try to show you in three different ways how stochastic models will play a major role. And I will do this in the way I usually do as applied mathematician, by showing you simplified, well-chosen, difficult prototype models to demonstrate these issues. So my main collaborators for the talk I'll give today are Boulem Kuder, where we'll have a little review of the stochastic multi-cloud model with a different emphasis, and then a current postdoc of mine for Themi Sopsis, who's at the Quran Institute, but he's already accepted an assistant professor position at MIT in mechanical engineering, and still is my postdoc, and Ian Grooms, who's also my postdoc. So we're entering a new era for stochastic climate modeling. We're interested in modeling crucial, poorly represented processes in contemporary GCMs. So the one we've been talking about at this meeting, with nice lectures by Boulem Kuder, by Sam Steckman, by Mitch Moncrief just previous, is one of the key ones is intermittent organized tropical convection. But however, if you're a climate modeler and you think about the ocean, current models at the highest resolution for the ocean are eddy permitting. For the polar oceans, you have Rossby radius of 8 kilometers, 6 kilometers. You're never going to be resolving that, yet these are decisive areas for poleward transport of heat, so mesoscale and sub-mesoscale eddies in the ocean are also a really important target. And you may be thinking, the second thing I want to tell you about is right now let's think about what quantification of uncertainty is. Right now we have a few models, and we try to quantify uncertainty by running a super ensemble or maybe a small number of ensemble members. Yet what you'd really like to do is for the changes of external forcing in various scenarios to calculate the means and the variances of the perturbations as a rigorous uncertainty quantification. One way to try to do that is Monte Carlo simulation with all the random states you have, and right now we can only use with our largest supercomputers 15, 20, 30-member ensembles, 50-member ensemble maybe in the future. That's not enough. So I'm going to talk about alternative ways to quantify uncertainty, and I'll talk about it in the context of simple mid-latitude models. Okay. And then another issue, and this is of primary importance in the ocean, actually, because there's tremendous backscatter of the mesoscale eddies, which are far more energetic than the mean circulations in the ocean, on the large scales in the ocean, in their heat transport. But it's also well known in the atmosphere. You want to represent unresolved stochastic backscatter from small scales to large scales in mid-latitude dynamics to increase variability of GCMs. And Tim Palmer and a group at ECMWF has been pushing it. Jorgen Fredrickson has done some beautiful work with his group in Australia on this, and Judith Berner has the nicest paper from ECMWF on how to do it. And these are engineering empirical things. I'm going to talk about more systematic ways to do these sorts of problems with more applicability. So from an applied math perspective, what can we think about? Well, we can think about multi-scale asymptotic modeling, and I've already, please come in, don't worry, you're not interrupting, have a seat. Which I've already talked about in my first lecture. There's a group of us for many years who've been looking at stochastic models for low-frequency dynamics for the principal teleconnection patterns, such as the North Atlantic Oscillation, the Pacific North America pattern, etc., and their role. and trying to find reduced stochastic models. So I actually began the program with my two collaborators in a Proceedings of the National Academy of Science paper in 1999. There's a very nice survey paper by Tim Del Sol on linear stochastic models. And then there's a whole special issue of Philosophical Transactions of the Royal Society of Palmer and Williams, where there are contributions, including one by myself and Boulem Kuder and Christian Franzke from 2008. Now, Mitch has already primed the pump a little about superparameterization. So superparameterization is not yet a practical method because it's too expensive. It's had a great success for enhancing variability for tropical convection, but I will propose by the end of the talk new ways to do superparameterization which will help you do mesoscale and submesoscale eddies for the ocean. And it's a different way of thinking about superparameterization than was traditional. But I first want to mention the traditional comments. So the people who deserve the credit for superparameterization are Wojtek, of course, but Piotr Smolarkiewicz. They wrote a very nice paper where they suggested it's better to think of a computation and demonstrated that it's better to think of computational strategies where you don't guess a closure but compute it on the fly from solving reduced model problems. And that was the theme in 1999. Then Wojtek did this very famous paper in 2001 where he used the theme from that paper to demonstrate the MJO-like behavior, which Mitch talked about in his talk. And I gave a mathematical framework for how to do superparameterization using multi-scale modeling for tropical convection in 2007. Then I want to mention some work my postdoc, Yulong Jing, myself, and I did, because this says something about the power of superparameterization. So the methods we discuss here are 1/30th as expensive as conventional superparameterization, and they are sparse not only in space but also in time. And these were tested. This is a very good instructional paper. So what we did is I designed a suite of squall lines with jet shears so that as you weakened the shear, you went from very organized squall line propagation to scattered convection. Then we had this reduced sparse space-time superparameterization algorithm and asked, could it capture the deviations and the organized behavior and the transition to disordered scattered convection? And it succeeded even though it was 1/30th as cheap as running the direct simulation. And I want to point out how coarse the simulation was. So these were mesoscale systems we were simulating. So on a 32-kilometer mesh, of course, you got no mesoscale organization. The superparameterization itself, the sparsest one we did had only 6 grid points and ran for 1/6 the domain and time. That's why it was so cheap. So if you think of 6 grid points, you're really doing a stochastic model. You're not doing a deterministic model in the small scales. Yet we were able to reproduce really tough patterns like the velocity and the specific humidity in the squall lines or when they failed with this super cheap resolution. Now, finally, I wanted to mention what we're planning to do with the very nice simulations Joanna Slavinska did, that with Olivier Paulwy and myself, we're planning to use them as a test bed for parameterizations. In particular, we have ongoing work to check how well superparameterization does there. So those very nice Walker cell simulations with intraseasonal variability. So the lecture itself will have 3 topics. So the first one, it's a nice way to go from, so Sam Steckman and Boulem Kuder gave really nice talks where Boulem's talk was about the multi-cloud model and the stochastic multi-cloud model, and Sam's talk was dynamical models for convective momentum transports and exchanges of the chicken-egg question of the waves and mean flow, and then stochastic models. Then Mitch gave a talk about his dreams about how he hopes people will attack coherent convective parameterization. And I want to make a comment, and I'll reinforce the point, that actually the strategies that we have with Sam Steckman and with Bulem Kudar are already stochastic modeling strategies addressing the exact points Mitch wants to address in operational models. They have the same multi-level heating, the same sequences of organized convection, the same properties of multipolar heating, and all of those things built in. So I will spend 20 minutes, if I can, talking about a little bit slightly different angle and a review on our stochastic multi-cloud model parameters. Then I'll talk about uncertainty quantification, and here think of mid-latitude climate change issues. And then I'll show you stochastic superparameterization in a toy model for wave turbulence, an extremely difficult toy model. And I'll just mention, I won't have time to say it, we have a paper we've just submitted to the Proceedings of the National Academy where I'm not exaggerating. We get phenomenal results for test models for oceanography in low latitude, mid latitude, and high latitude regimes for this. So that'll be the plan of the talk. So using the stochastic model, multi-cloud model to improve cumulus parameterization. So stochastic, and people can stop me during my talk anytime, by the way. This is a small audience. So a stochastic multi-cloud model for organized convection. We're going to take the multi-cloud model in. We've been arguing that it's a good model deterministically, but we're going to run it with very bad parameters so it will behave like a typical GCM. And then we will stochasticize it and show you how much its variability improves. So we're going to do something silly as far as the stochastic multi-cloud model. We use it as a demonstrator. And specifically, I want to concentrate on showing how much we improve the convectively coupled wave structure and get the kinds of structures that people like Wojtek and Mitch have talked about from very comprehensive CRM models by methods that are millions of times cheaper and that are the kinds of things seen in nature also. So here are the papers where you can find this material, and there's a further paper in climate dynamics that's just been accepted. Well, why a stochastic model for convection? You want statistical self-similarity across scales. You want to understand how cloud systems interact with each other in their environment. You want to really capture these coherent structure, mesoscale convective system deviations from the traditional quasi-equilibrium paradigm and standard parameterizations, like Betz-Miller or Arakawa-Schubert or Zhang McFarlane. So you want to improve the tropical variability in climate models realistically to reduce model error. So as Bulem had already talked, we'll propose a stochastic model for the area fractions of cloud types. So I don't have to say much to the audience about this diagram because it's been well said. Above the standard boundary layer clouds, clouds that penetrate above are congestus clouds, deep clouds, and stratiform clouds with evaporative cooling from rain falling through subsaturated air below them. So in a dry environment, a rising parcel entrains a lot of dry air and never reaches even the theoretical height it could rise with a moist adiabat. Whereas in a moist environment, a parcel will tend to rise much higher because the moisture has preconditioned. So a dry troposphere with positive CAPE favors congestus clouds. Deep convection is allowed beyond the freezing level when the troposphere is moist. Those are two of our driving principles. So we'll have 4 kinds of sites for clouds within a grid box: clear sky, congestus, deep, and stratiform. And we're going to have a sequence of 4 states at a multivariable Markov chain, exchanging the behavior amongst these states let's see, I don't want people to stand outside the room. There's one more chair here. Two more chairs. Okay. So, and what we do is we have these intuitive transition rules, and some transitions are forbidden. For example, clear sky never turns directly into stratiform rain. That's a forbidden transition. And that's, of course, physically, you guys would think I would be crazy if I told you there's a transition where clear sky made stratiform rain. Sure. So I will tell you more about that. Don't worry, that will be explained. That's just to warm you up. Okay. So here are our intuitive transition rules. A clear sky site turns into a congested site with high probability if the CAPE is positive and the middle troposphere is dry. A congested site or a clear site turns into a deep site with high probability if there is high CAPE and the middle troposphere is moist. And a deep site turns into a stratiform site with high probability. All three cloud types decay naturally according to prescribed decay rates. So this is what Boulem talked about. So here are our four states. So conditional on the large scales. We have a four-state Markov transition. The zeros mark the forbidden transitions that I talked about. The non-zero ones are here. So this is your question answered. And what we do is we have two CAPEs, a low-level CAPE, a boundary layer CAPE, and a middle conventional CAPE, and we have a measure of the dryness. And we have the intuitive transition rules that the model depends in a kind of Arrhenius kinetic style way on products of these. For example, to go from clear sky to congestus, the middle troposphere has to be dry, and you have to have positive boundary layer CAPE. And then you'll create that. So it's very intuitive. And we picked intuitive transition times for these. So the transition rates depend on the large scales. Of course, they will provide information to the large scales themselves. So there will be a two-way communication from the stochastic model. So a way to design these things is to test by an equilibrium distribution conditional on a certain large-scale process. And then, as Boulem spent a lot of time talking about, there's even a way to get a deterministic closure in the limit of many, many parcels of this. So that's a deterministic mean field. So you can start out and get a deterministic closure that will happen in the limit of a huge number of sites. So this is all very systematic. Now, here I want to show you, here's the evolution in one of our equilibrium things, and this is identical to Boulem's slide, but I want to point out one thing. So here's the equilibrium fraction of clear sky predicted. There are analytic formulas for it. Here's the one for congestus. Here's the one for deep. Here's the one for stratiform. So we have fluctuations about the equilibrium, but notice because of our intuitive transition rules, we go from a bump in clear sky dynamically to a bump in congestus, to a bump in deep, to a bump in stratiform. So there's causality here of the dynamics, even in equilibrium. We will be very far from equilibrium when we apply these things, of course, because the mean scales will be responding to this model. So now we're going to pick the deterministic multi-cloud model in a bad regime. No, they depend, the results, not a great deal on any of the model parameters we've had, and we've even checked our intuitively guessed parameters, as Boulem said, fit Darwin and Kwajalein data, two very different tropical data sets. So not very much, although we haven't explored all parameters. There might be some scenarios where one should change them. And in fact, we have a strategy of using Bayesian inference and Markov chain Monte Carlo to infer those parameters for data in general. And that's a thesis Michel Chavrotier is doing with us at Victoria. So that's a very important question. But right now, we haven't seen that great sensitivity. Okay, so people here have seen me and Boolem both talk about the multi-cloud model. It's a two-baroclinic mode model which has this dipolar heating vertically that Mitch is talking about, and it's dynamically active, and it's based on with congestus heating too. It's based on 3 cloud types. It's been validated to capture the physics and morphology of convectively coupled waves. We're going to run it in a stupid regime where it looks like a typical GCM, and we're going to run it in a Walker cell without rotation. And first we're going to run it deterministically, intentionally, to behave like a typical GCM. So a typical GCM will give you a regular, not very stochastic Walker cell. And if it has any convectively coupled waves, they'll be very regular and move along and not really have much intermittency. So that's our model we're going to add the stochastics over it to. Now the wave structure of the convectively coupled waves is upright and not tilted at all. And that's also typical. If they have a convectively coupled wave, it doesn't have the correct physical structure. People in the business know convectively coupled waves are tilted in the direction they go from having a congestus pre-side to a deep side to a stratiform side, and are highly tilted. So this is now we do the stochastic multi-cloud model just with our intuitive parameters. Our Walker circulation, which looked trivial, if you remember Olivier Paulwy's tripolar Walker circulation statistics, this is the same kind of tripolar Walker circulation statistics that he got. And here's the heating, and then here's the variability. And the precipitation, you see, is very, very similar to what were in the CRM simulations of Wojtek-Grabowski. Now, what I want to emphasize here is the wave structure. So, now we're on a scale, these are thousands of kilometers, 23,000 to 31, so we have 8,000 kilometers here, and we're expecting, associated with this kind of variability, perhaps convectively coupled wave trains with embedded mesoscale-like systems in them. And that's what we have. So here is just looking at a typical time shot. There's no averaging of one of those systems, just focusing on it. This one happens to be going westward. There's no rotation, so it's irrelevant. So I want to show you the cloud fractions. So here you see the first lead cloud fractions, this system overall, here's its large-scale behavior. It's a very nice-looking tilted convectively coupled wave with shallow heating in front, stratiform heating behind, and deep congestus heating going on, just as you'd see in a typical observational convectively coupled wave. And look how beautifully the stochastic multi-cloud model, so these scales are mesoscales. So you have a wave train of mesoscale convective systems embedded inside of it, analogs produced automatically by the stochastic multi-cloud model, where in the leading edges, congestus area fractions dominate. Those are the green. In the intermediate areas, deep fractions dominate. And in the middle and trailing areas, stratiform fractions dominate, just as nature would show, and it's intermittent and irregular and fluctuating, and produced by the parameterization from a model that had none of this right. So this plus the version of CMT we have that Sam talked about are ways to address exactly in a dynamical way, the ways to systematically improve GCM. So I mentioned this at NYU Abu Dhabi. This is our first project. And we have a proposal with Partha into Monsoon Mission, trying to improve the operational model also in the same way that people use. So the conclusion of this part was really just to reiterate and emphasize some different things than Boolem did, that we presented a strategy for stochastic modeling framework to improve parameterizations, and exactly focusing on the fact that intermittently you will get organized tropical convection, and you need to respect that, as Mitch has been emphasizing for many years. The model is attractive. We don't model the mass fluxes, we model the area fractions. So if you have a closure procedure that produces a nice model for vertical velocities that can be combined with area fractions in a nice way rather than just having only the max flux. And we showed that both the variability and wave structure were improved. So we have several papers on this on toy models. Now we're ready to try operational models in idealized settings. So the second topic is uncertainty quantification for turbulent dynamical systems. I'm leaving the world of tropical meteorology. So we should think of dry dynamical cores in mid-latitudes at 200 millibars, 500 millibars, way up in the upper troposphere, where people try to make predictions about what will happen to the jets and what will happen to climate change and things like that in mid-latitudes. And in fact, I will use so what we have in all of these systems is the following kind of structure. We've got an external forcing. That produces a climatological mean state. If we examine the stability properties of that climatological mean state, it's always unstable. It's maintained by eddies that rectify it. It's always unstable. So that means it has some unstable modes, and the role of quadratic nonlinear terms of fluctuations is to transfer the energy that's being created by the unstable linear modes to the stable modes through nonlinear processes so that a balance is achieved. A statistical balance is achieved. That's what's happening. So there's a central role for the nonlinear terms. Now there's a group of people who qualitatively model the atmosphere as linear stochastic models. That's not the goal. There's some success with that, and Kim Dal-Sol, Prashant Sardeshmukh, Brian Farrell are leading advocates of this, but they're interested in qualitative models. For uncertainty quantification, you want a quantitative model, a model that will produce the response to the changes in means, the response to the changes in variance, a quantitative model. So you change the external forcing in some way. You'd like the responses to be known by a model that's much simpler. So our alternatives now are to do small number of ensemble simulations. So we need a new way to think about these kinds of problems for uncertainty quantification. And the way I'll think about them in this lecture, since I have the luxury of being an applied mathematician, I have tenure. So what we'll do is think about it today in the context of a very prescient model developed by Lorentz. So Lorentz's most famous model within atmospheric science is this model. His most famous model outside atmospheric science is his three-mode model. Everyone who knows his three-mode model, who knows atmospheric science, knows it's a terrible model for the atmosphere. But it's a spectacular model to show that it's a great model to illustrate chaotic dynamics in a deterministic system. This, on the other hand, is a 40-mode model, which is a great model to illustrate baroclinic turbulence in the mid-latitude atmosphere. And I'll just articulate what it is. He thought of having a mid-latitude circle. The Rossby radius, synoptic scale Rossby radius for a mid-latitude circle will give you about 40 points. He thought of discretizing nonlinear advection in this strange asymmetric way of a single variable so that you'll have the propagation from west to east that we know happens in the systems. Then he has the natural damping, and then he has external forcing. So this 40-mode system, Lorentz designed to mimic baroclinic turbulence in the mid-latitude atmosphere. This system is extremely popular and used for data assimilation, for fluctuation dissipation studies, for predictability studies. It's an extremely popular system. He picked the value f equals 8 for the forcing, and I just want to emphasize that this is a fantastic system to study different turbulent regimes. So when you force less than its traditional value, you get a very wave-like regime where the turbulence propagates with group velocity eastward and phase velocity westward, just like Rossby waves. In the strongly chaotic regime, you've got the same kind of behavior but less organized. And then in the fully turbulent regime, a similar behavior, but even less organized and much stronger as you drive the system. Yes? That's the whole point. Deterministic systems, which are large dimensional, are very different from three-dimensional, say, deterministic. The chaos in the three-dimensional Lorentz model is not the chaotic dynamics of these systems. Great question. That's what I want to hear. This model, for example, is 40-dimensional. It already has 16 unstable Lyapunov exponents on the attractor. This one has 18, and this one has 22. So the kinds of systems I'm talking about have a huge phase space dimension, have a huge number of positive Lyapunov exponents. And on their large scales, they acquire stochasticity without being stochastic. And I have many, many examples in my work where I've demonstrated that in recent years, on what's called the truncated Burgers-Hoff model, on this model, on other models. So you can use the ideas of dynamical systems to quantify how stochastic these are. And these are way in a very different stochastic regime. They're strongly mixing. They have rapid decay of correlations. They don't have high symmetry. Lorentz 63 has very high symmetry, very weak decay of correlations. So these are very different beasts. And these are the beasts of climate science we have to deal with. So it's a different thinking. So deterministic systems can acquire stochasticity. I have a book called Information Theory and Stochastics for Multiscale Modeling, based on a set of lectures I gave in Montreal. If you go to my website, look at that book, I have a simple example there of how a deterministic system can acquire stochasticity. But I have many examples, many, many examples. So that's the point. We will make an intelligent approximation. So the first attempts are essentially the attempts Sardish, Mook, and people have tried. So you have the linear operator, which is an object you know very well because you know its climatological mean, and you have in nature the real nonlinear energy transfers. You want to find a statistical model that will mimic this process, but is vastly cheaper than solving the whole equations and doing ensembles with it. So the first guess is to ignore this and stabilize this by additional dissipation, and that gives you a closure which won't work very well. And I don't want to spend a lot of time on that. What I do want to spend a lot of time on is how to make a modified quasi-Gaussian closure method, where what we're going to do is replace these nonlinear terms by a statistical model for them.
How strong is the nonlinearity?
Unbelievably strong when f is equal to 16. These are not weakly nonlinear at all. So the weakly nonlinear regime for the Lorentz 96 model ends at f equals 4. This is f equals 6. It's already very turbulent. F equals 8. You're very far. The nonlinearity is very... So think of forcing this system when f is 16. You've got this... The Reynolds number is incredibly high here. I'm sorry? Just more intense events. These are intense spikes of U. So it's generally wave-like with intense bursts of activity. Generally wave-like with intense bursts. I'm sorry? No, the forcing right now is a constant. These are constants. Later on, I will try to see if I can predict the response to a climate change forcing, which will be stochastic or deterministic or anything. It's a new, so I have nonlinear response theories based on fluctuation dissipation ideas, but I'm not going to talk about them. I'm going to talk about an alternate way to do the grand problem all the way. Do it all the way without going through fluctuation dissipation response. So that's a fascinating topic, but not, so I'm glad I'm provoking a lot of discussion. This is great. So now let me go to my point here. So what we want to do is replace these nonlinear terms by something vastly cheaper that will still model them for uncertainty quantification. So we know, just as in turbulence, there's an exact equation for the second-order statistics, which depends on the third-order statistics. It's a formal closed equation. You can write it down. Here it is. The covariance operator changes by the linear operator. Forget this. This is if there was additional noise, plus a term Q, and Q is a functional of the third moments of your system. Now, in general, you don't know the third moments of your system, but I claim for almost every geoscience system, you know the third moments at equilibrium a priori, at equilibrium, at the unperturbed equilibrium. Here's why. Because let infinity be that unperturbed equilibrium, you know the linear operator at the climatological mean state, and you know the variances at the climatological mean state. So this plus this determines Q infinity. Now, the typical way people have used linear stochastic models is to damp everything. Then you don't even recover the climatology correctly. So what we're going to do is think a little bit and think of this cycle, and make a very precise way. And this can work for very complicated systems. In fact, we're trying them right now, these minutes, on T21 truncation, barotropic, and baroclinic models on the sphere for the atmosphere. So look at the positive real eigenvalue linear terms. Then clearly there should be some dissipation associated with those. These guys that are negatively damping, there clearly should be some amplification, some noise driving those. So how can we do that systematically? So here's what we do. This is a known symmetric matrix. Split it into its positive eigenvalues and into its negative eigenvalues. For the negative eigenvalues, represent them as an effective damping. So represent them as a nonlinear effective damping. So this is the formula they would give in this thing if you had an effective damping, and here's the solution of that equation. So we know QF minus at equilibrium. We solve it here. The important symmetry of the cubic terms is that the trace of them must be zero. That's energy conservation. So keep that symmetry in QF plus by scaling it this way, and that scales the problem perfectly with climate consistency at equilibrium. And now let's make a simple nonlinear dynamical system where these quantities will respond to the uncertain covariance far from equilibrium. So we do that. So here's this formula. Here's the formula to get QF plus. For numerical stability, we add a small amount of Q here because the minimal operator will have a zero eigenvalue, so it won't dissipate exactly. So we do that. And then we have a choice. We just say at the given time we'll use the energy functional of the covariance, or the sum of the typical deviations. So in summary, instead of doing Monte Carlo simulation, we're going to have an intelligent design, wave mean flow closure that automatically will compute the second order statistics. So here's how we get the mean. Here are the eddy fluxes on the mean that rectify it. Here are the covariance terms in our modified closure. We're running really a nonlinear closure model. Here's N, the additional damping. Here's the additional noise forcing. This is computed on the fly from this. This is computed on the fly from this. And the only thing we've done is calibrate by the climatological mean state. That's all. I just told you. So it's modeled precisely by taking that flux QF minus and asking what would be the contribution to damping for it. So the contribution to from a damping operator for it would be this. This has negative eigenvalues. This is a positive definite matrix. It's very easy to prove that the solution N infinity here has negative eigenvalues. And the solution of that is here. So we take the equilibrium one and model it there. Away from equilibrium, we model N by the ratio. So we know that N should scale. N is that n should scale with the square root of the energy because of the cubic term, because the variance is scaling with u squared, and there's a cubic interaction in the term. So this is dimensionally correct. So we picked that dimensionally correct scaling. We threw it away to make it cheap. We don't need to compute it. We calibrated it at the climate. And we want to do climate change without running huge ensembles. So that, and that's the climate. It's you take the statistical mean average. This is something everyone computes. You're not on the attractor. This is a big advantage. It's what everyone knows, and they know the linear operator at that state pretty well, at least in a model. I'm not talking about nature. I'm talking about models now. Okay. So, by the way, since there are mathematicians in the audience, what emerges from this system are a lovely new kind of non-local stochastic ODEs for uncertainty quantification. And here is the formal stochastic equation that gives these equations as in the dynamics. So that means the theory is realizable, but it would be very nice for some mathematicians to get interested and rigorously study the stochastic dynamics of these equations. Okay, that's a side comment based on my lectures. Now I'll show you results. And I want to show you how hard these test problems are. So what we're going to do is here is the Fourier equilibrium statistical spectrum for the L96 model. Here's in the toughest case, the fully turbulent case. Then it's hard for me to see my own slides. This is a problem. But I don't remember them. I didn't rehearse this talk. This is on the fly. Okay, no, I can't look at the screen. I'll try to respect your wishes, Vojta. Thank you. Okay, so what we're going to look at is here's the spectrum of 40 modes dynamically moving in time. Now here's the spectrum done with Monte Carlo simulation, where really we're doing 10,000 ensemble members to make a perfect distribution. Our initial equilibrium of spectrum is down here. It's very far from equilibrium. It has to adjust to this. This is the statistical equilibrium. So we're doing ensemble prediction by a closure, an intelligent design closure for uncertainty quantification. Now, here is the total variance being tracked by our modified quasi-Gaussian closure, and here's the energy of the mean, and here's mode by mode. So I challenge you to actually see any discrepancies. So here's our model. It's really, I'm not kidding you, a million times cheaper to run. It has the cost of 2 ensemble members. And we're tracking the same statistics here and eventually getting to this state from this state statistically as we look at the modes. Another test case, suppose we now let's start doing climate change. We didn't have the seasonal cycle in our model. Let's put in a seasonal cycle and see by calibrating at the base state we can recover the effects of the seasonal cycle, the means and the covariances predicted by the closure. So here again is the spectrum with the Monte Carlo simulation. It relaxes to this periodically repeating pattern. Here's the spectrum with the MQG, starting from the same value but with time periodic forcing. And we see that this is the track, and we've done an incredibly good job of following it. Now, here let's do something that's more like a climate change scenario where the forcing is random. So the forcing, the mean value is at 16, but we know that for calibration, but our climate change forcing is doing something like nature, wiggling randomly. Can our simple closure respond there? And again, in the picture norm, I challenge you to see any discrepancies. Okay. Now, let's pick a weakly chaotic regime, which is a very tough test case, and pick a random forcing with f equals 6. So here the spectrum lingers for a long time. It has longer correlations, takes a longer time to adjust. It's random forcing with typical 20%, 15% fluctuations, we start very far from equilibrium, and again we adjust. Now, let's pick the craziest time-dependent case. This is insane. We're calibrating at f equals 10. Our forcing is going to fluctuate between 20 and 0. At 0, our system is weakly chaotic with no positive Lyapunov exponents even or at 0. At 30, it's hugely turbulent. We're calibrating with 10. And I'm going to ask whether we can quantify and track the uncertainty and the variance for each one of the 40 Fourier modes. And we've done it. So here's a method that's literally 1,000,000 times cheaper than Monte Carlo simulation and has managed to quantify the uncertainty for changes in forcing by simple, intelligent design calibration using third-order statistics in an intelligent way at the equilibrium state we started from. Now, I don't expect this kind of performance in more comprehensive models, of course, but I'm very happy if I get roughly this performance. Anything roughly within this is a huge advantage over operationally trying to run individual ensemble members. So this is what we're heading toward, and we're working right now with Christian Franzke on T21 barotropic models and T21 Marshall-Molteni three-layer baroclinic models. We're using this idea. So we've managed to do climate change by solving an extremely simple stochastic nonlinear model instead as a surrogate for it with stochastic statistics. So that's what I've said here. We have a series of papers. And by the way, you can break this thing with L96, but you need an insane inhomogeneous anisotropic huge forcing to break this. And it's done in one of the papers. So we have a series of papers which are on my website on this project. So in the last 15 or 20 minutes, I want to go back to this very great idea that Wojtek and Piotr Smolarkiewicz had about stochastic superparameterization and demonstrate it for you on a model for wave turbulence. And this model for wave turbulence is the simplest model I know with what we dealing with what we have to confront all the time in climate science. Namely, in a lot of engineering turbulence problems, energy cascades downscale. In climate, atmosphere, ocean science, there are instabilities at small scales. Coherent structures cascade down to small scales, but they excite other processes, like wave processes, which cascade energy back to the large scales. So there's a highly non-trivial inverse cascade of energy. So I'm going to talk about a very simple-looking equation with very complex features for turbulence, which has those features in it. And we will test a new way to do something which Ian Grooms and I call stochastic superparameterization in a model for wave turbulence. And when we apply it to two-layer quasi-geostrophic models in ocean regimes for mid-latitude, low-latitude, and high-latitude, it will be statistically accurate at 350 times cheaper the cost of running a direct model for mesoscale turbulence in these prototype ocean situations. That's the gain you will get. 350. So a few minutes versus a few days of simulation. So it's based on a different take on the ideas of superparameterization. And in fact, it's a stochastic seamless superparameterization. We don't introduce little periodic boxes and solve the problem on periodic boxes. It's done by a semi-analytic procedure I will describe. So first of all, I want to write this mathematically as a schematic set of equations. The schematic set of equations, I'll have a generic variable u. Typically, we'll have linear terms, quadratic terms. I want to keep the cubic terms here. Source terms due to moisture aren't cubic, but they're nonlinear like this. So turbulence theory 101 is we have a mean and we have fluctuation. So we can write an equation for the mean, that's exact, and an equation for the fluctuations, that's exact. So let me do that on the next slide. So the mean equation is ugly, but it's exact. And it involves the fluctuations about the mean. So I'm calling the equation for the fluctuations the eddy equation, although there may not be any eddies. And that's the equation for the fluctuations involves the key thing, a linear operator, conditional on u bar, for the fluctuations, plus various nasty nonlinear terms here, where this is what L of u bar is. So it's centered about the time-varying mean state you have. So these are exact equations for the mean and the fluctuations, equivalent to Reynolds' famous equations for Reynolds averaging that are more than a century old. We can just do this all the time mathematically. Now, where will superparameterization come in? So this is my own take on superparameterization. I will supply some references by the end of the talk where you can read this, about this. And partly my thinking is what we need as mathematicians is a flexible way to think about new numerical algorithms for really stochastically irregular systems. And that's what I'm trying to do. So the first approximation we'll make is a Gaussian closure approximation. Now, this doesn't mean the field is Gaussian. It means conditional on a large-scale value, it's Gaussian. This is a very different statement than saying it's Gaussian. So what we're going to do is replace the eddy terms that are nonlinear in U prime by a stochastic forcing. This is a quasi-linear approximation which guarantees Gaussianity of the eddy statistic. The second thing we're going to do, and this is the spirit of superparameterization, we're not going to consider that for the whole field. We're going to have a pointwise value of the field and compute this for each pointwise value locally. So that's like superparameterization of the conventional sort. Now, we're going to be doing this in problems which are not the traditional problems where people invoke separation of scales. This conditional system will have instabilities in it naturally, depending on U bar, and they won't saturate. This is the same thing that happens in superparameterization with moisture. You have these moisture triggers. They weren't really going to saturate if you ran them as an equilibrium problem. They're just transient triggers to let you proceed and go to the next state. We will use them in this way too. So we're going to do this despite the fact there will be exploding eigenvalues for L of U. So here's the general derivation then. So once we make the superparameterization approach, yes. Yes, sir. That's right. It's in that spirit, except we're going to be using it for very unstable flows with upscale cascades of energy in a numerically efficient way. You're right. It has some connection with rapid distortion theory or something in some ways, but it's a different. It's used in a different way. But you're absolutely correct, Radha. So now we just have to solve this eddy equation conditional on the large scales. And you can solve this. We don't need it because, as Amit already found out, sorry, I flipped to the wrong one, we just need the covariance of the field here, not the details of the field. So when we want to use it in a superparameterization algorithm, here's the equation for the field itself. Here's the equation for the covariance at each Fourier wave number. And this is a standard bit of elementary stochastic analysis. And then we integrate from minus infinity to infinity in the Fourier domain. And that gives us the needed quadratic terms for the flux, for the feedback. So these guys depend on the large scales and not with white noise and time, with memory and with instability. This is a key difference. But they're just calibrated that way. So now here's how we will test it. We will test it on a strange-looking equation. And the name is the MMT equation. And Vladimir Zakharov, the famous physicist, name this equation for Majda, McLaughlin, Tabak. We are not arrogant enough to name the equation for ourselves, but he named it because he really liked our work, and we wrote a paper in 1997, which appeared in the Journal of Nonlinear Science, where Vladimir Zakharov and his group have worked for 25 years on wave turbulence. And their theories for wave turbulence were never really tested anywhere. So I said, what's the simplest model we can design to test non-trivially wave turbulence theories? And it's this model. So I'll tell you what the features are. Psi is a complex, so think of nonlinear quantum mechanics, but this has nothing to do with quantum mechanics. Psi is a complex field, has a real component and an imaginary component. If you know what the dispersion relation is for ocean waves over deep water, you get a square root dispersion relation. This is extremely important. If you had a squared dispersion relation, you would not get any of the behavior we're talking about. So I picked the square root dispersion relation when we cooked up these models. I cooked them up because I knew that Zakharov's theories, the best chances that he reports they have of working is for deep water waves over, surface waves over the deep ocean. And I knew that this dispersion relation. Mathematically, this dispersion relation allows many, many resonances in one space dimension. A standard dispersion relation will not allow any. This is why it's picked. Then we have a cubic term. We'll pick the minus sign here. This will make solitons. Then we'll have some routine terms as we'd have in climate science. Large-scale external forcing and some small-scale dissipation. Don't need to describe those in detail. So this problem, as I will show you, includes a turbulent inverse energy cascade, coherent structures breaking as unstable solitons, and random stochastic backscatter to affect the large scales from the waves that radiate from when the solitons break. So it is one hellishly hard problem, and I'm not joking. If you're a turbulence theorist, you can play with regimes of the MMT models, which are somewhat more general than the model I've written here, and get every scenario of multiple cascades you can think of in turbulence in this toy model, and it's in our work. And in fact, the paper, this shows it. So here, our perfect truth model will be 64 squared points in one space dimension. So that's 8,000 points. So that's nature. And now I just want to point out how fantastic these models are. When the external forcing F is 0.0163, you get, here's the logarithmic scale for a turbulent energy spectrum, and you get a spectrum. Notice this has power that's 1.5 decades less than this at the large scales. And you get a cascade exponent that's k to the minus 1. This is only a pure downscale cascade. Now change the forcing slightly in the fourth decimal place, and you go to a violent inverse cascade. And by the way, this spectral exponent is predicted by weak turbulence theory, and this one is the inverse cascade exponent predicted by weak turbulence theory. But notice we have 1.5 decades of those spectra there. So that's the power of a one-dimensional model. Now physically, when you look in physical space, it's doing exactly what I said. Here are the solitons collapsing and radiating energy on our domain, breaking and radiating energy. Okay. So what you have, and the paper to read about the MMT models besides the original one is a paper of David Kai and myself and McLaughlin and Tabak in Physica Dia in 2001, which is an honorary journal issue for Zakharov's birthday. I think his 60th birthday.
Do you also have a weak oscillatory part in the profile of psi?
I'm sorry?
Weak oscillatory part is
No, it's a stationary forcing at a given spatial wavelength. That's not a, we could easily do that, but we're not doing it here. We're doing the simplest problem. So here's what we have. You have the forcing range, which is that constant forcing at large scales. You generate these coherent structure solitons. They want to collapse as they grow and go to the dissipation range. As they collapse, they radiate back energy and affect the large scales. This is a hellishly hard problem, we're going to cut it. We have 64 squared grid points, and we're going to cut it at only 64 grid points. So we're going to use 1/64th the resolution and see whether we can capture with stochastic superparameterization an improved spectrum. So it's a really tough, simple test problem. So here I'll quickly run through the details. So here is the mean equation. Here's the Eddy-Fourier equation. You can solve them. What I want to point out is they're non-normal equations, first of all, so they have transient growth. Secondly, they have instabilities whenever your conditional mean value is between psi bar to the fourth and 9 psi bar to the fourth. So they're not equilibrating in any conventional way. And we run them with reasonable values for everything. Our only adjustable constant will be our initial value for the covariance as we do the superparameterization. And it's the pre-constant with a 5/6 spectrum. So we do that. And here's the result of stochastic superparameterization. So our models are so cheap here that we can actually compute the eddy terms as a closure from running superparameterization and simply evaluating with a lookup table what the values are. You can do that. You would never guess the closure we have. So there are 3 quadratic terms in the system. One is easy, because one is just a phase renormalization. That's the value of psi prime squared. That's here. But I challenge anyone in the audience to a priori guess the closure that you need for the real part of psi prime squared average. What it is you see, as you move out in radius, a wave number 2 nonlinearity centered around the unstable bands of the system. This one, once you know, is easy to guess, this one, because this one's just rotated 90 degrees from that one by symmetry. But this one, I challenge anyone to guess it. I have no idea where I would have gotten it from. That's the whole point of superparameterization. It's done the thinking for you. You only did thinking to make an intelligent numerical method. It did the thinking for you. Now, you can't do a lookup table, by the way, for ocean turbulence, so we don't do that here for ocean turbulence. But now I want to show you the improvement. So now we're going to run, we have nature with this huge inverse cascade, our surrogate for nature, with 64 squared points. Now, of course, if you ran the same model, just truncated, this is with 64 squared points, with that cascade that keeps going down here. Here is, you have to add some dissipation to the model with only 64 points to get it to run at all. And this is the best result we could have for that model. So you see you're 2 decades off in energy. It's lacking all the energy if you just ran the bare model. You run the stochastic superparameterization closure and a miracle happens. You've raised up all that energy to essentially the same values here. We didn't try to optimize to take care of these few wave numbers. We wanted a fair test. But you can see we've almost reproduced the effects of the inverse cascade without putting it in. So that's a spectacular application of subgrid scale resolution with an inverse cascade, typical for geoscience problems. And so let me end, because I started late, so I'm talking 1 hour right now. So there's a general framework for stochastic subgrid scale modeling with no scale separation, no small scale equilibration. It's based on a conditional Gaussian closure approximation and a point approximation. There's success in a difficult test problem with no scale separation, coherent structures, dispersive waves, and an inverse cascade from highly unresolved scales to the large scales. The cost of pre-computing the eddy terms is negligible in this problem. We could just run this problem as much as we want because it's so cheap. And we got a closure that performed amazingly well that I wouldn't know how to predict. So what are the 3 references? So the 3 references for this work are a stochastic superparameterization and a one-dimensional model for wave turbulence. And then this philosophy of how to do superparameterization I actually highlighted in another paper, which for the 75th anniversary of the Quran Institute, we were asked to submit overview papers for our field, so I wrote one, and it's called Challenges in Climate Science and Contemporary Applied Mathematics. I hope some of the mathematicians here will read it, and there I advanced this strategy for superparameterization we tested here, among other things. I also discussed fluctuation dissipation ideas and how to improve imperfect models. And this predates something that a mathematical test model for superparameterization I made up, which is a test model for exactly all of the issues of superparameterization. And then I want to mention a fourth reference. One advantage of the superparameterization techniques is you beat the curse of ensemble size. You can only run small ensembles in general, and if you can use stochastic superparameterization, you can run it in data assimilation with huge ensembles. So John Harlem and I tested stochastic superparameterization in a data assimilation context. And you get fantastically interesting results with huge improvements by using it. And that's the fourth reference I should have. So we have a paper with John Harlem on using these things for data assimilation. And it works amazingly well. And I'm sorry for being so exuberant, but it's true. I'm not lying. So with that, I'll end this talk, and I hope everyone realizes my theme is to throw new ideas out for the community for the future agenda, which is how to cope with cursive ensemble size for data assimilation, prediction, uncertainty quantification, and increasing the variability of nature, of models to look more like nature. Okay, so with that, I'll end. Thank you. Yeah, there were great questions during the talk, so maybe there might be. So let me challenge the young students, first of all. So there are a lot of young students here. Let me challenge some of you to ask a question. Are you a young student? You look too old to me. Are you a young student?
Well, I'm doing my PhD.
You're doing your PhD. Everyone doing their PhD is young to me. Okay, so fair question. Are you a mathematician or a meteorologist?
No, I'm from the physics department.
Even better. Okay, I'm happy you came. So ask.
I didn't understand why you have the functional has a third order term inside.
Where?
Okay, if you see the equation of motion, there is a second order inside term.
Okay, so let's go back. So you mean the MMT equation? Here we go. I did this because when you do wave turbulence, they do a Hamiltonian preconditioning transformation, and the first term that comes up is a cubic term. So this is the simplest model that does the Hamiltonian renormalization, which has that feature. And this is also a famous term if you know soliton dynamics. This minus sign makes focusing solitons.
So the energy functional has a term which is power 4 and the equation of motion.
Yes. So the energy functional, and it's discussed in the MMT paper from 1997. All the conserved quantities and their behavior are discussed. The energy functional has a positive definite term coming from this energy multiplied by psi squared integrated, and a negative energy term here. That's what creates solitons. That negative energy term creates the soliton. That's called the focusing case. If I switch the sign to plus, I would get the defocusing case. By the way, Zakharov's weak turbulence theories are invariant to whether you have plus or minus. And we criticize that very heavily because the behavior of the system is incredibly different whether this is plus or minus. And that's a built-in symmetry.
What's the value of D there?
D is just a general dissipation. We take it to just, since these are spectral calculations, we want a pure inertial range. We're forcing at the large scales, dissipating way at wave numbers, I forget, beginning at 6,000 or 4,000. This is way in the tail. And then we have no dissipation in between. It's a pure test of inertial range turbulence.
I think they are in your slides. I saw the D.
Yeah, but it's not a reviewing. I mean, it exists. No, this is the, it's not the D in the direct simulation. This is the D in the stochastic model. This is the D in the stochastic model, I know that. This is too much detail for the talk. Okay, that's a very good question from a student. How about one more question from a student? Not you. Another student. PhD student, another PhD student. How about one of my friends in atmospheric science, who I met last year, who I really enjoyed meeting? How about you? No. I think you got your PhD a number of years ago. You're not as old as I am, but
I'm not quite sure to understand all things.
So how about the first part on tropical meteorology and stochastic? See if you.
I still have that question. How does this match? How the time scales actually in general circulation models? We always use time scales for different processes to model. How does stochastic model help us in quantifying those?
Well,
for example,
the idea is to replace those time scales with other time scales.
Yes.
The time scales are the internal variability of the stochastic process.
Yes.
So if you recall, the deterministic multi-cloud model has a Betz-Miller, Arakawa-Schubert type parameterization for deep convection,
yes,
but it has these add-ons of stratiform and congestus. The stochastic one has those plus time scales for those processes. Now, as Bulem Kudar mentioned in his talk, I'll just repeat it, we guessed them for this work, but we now have work we're doing with Christian Jacob and Karsten Peters at Monash University in Australia, where they know very well the field campaigns over Darwin and Kwajalein, and we've used the stochastic multi-cloud model to see how well it compares to their data. And there, we're getting the time scales. And those are the time scales you should use. You shouldn't use the old time scales that are in the GCM. You should use the new time scales that are empirically matching the data. This is why when Radha asked me the question, how robust are these things, I don't know yet. We've checked 2 sites from Nature. One is an anomalous site because it's Darwin with the world's deepest convection because of orography and various things, and one is a standard MJO region, Kwajalein. And our time scales that we get empirically are rather close to the ones we have.
Can this method help us understand the timescales of radiation?
So you're asking an important question. So we have, I guess, thought about this more as NWP. It's a really excellent further research problems to add radiation to the thinking. So that's a really great research area. So we don't have active radiation in. And active radiation is going on a longer time scale. So other ideas could be used with it. But right now we just have Newton radiative cooling in all of our models. So see, you managed to ask 2 nice questions.
Thank you.
Others could ask questions now.
In the Lorentz case, the main assumption was about the third moment. Right?
Well,
so you showed results with the.
Let's go back.
Yeah.
So there was no assumption on the third moments. There was a calibration of using them indirectly. This is the important thing.
No, but on the previous layer,
Here.
this one, in the steady state, this.
This is the key statement. So here's what we did. This is an exact identity.
Right,
We added noise here, but it's not important. This is an exact identity that says the second moments change by a linear operator at the mean state times the second moments, which is called the Lyapunov equation, plus a contribution from the third moment.
Right.
And this third moment contribution is explicit and known in the model.
No, but the equation below that.
Now, so what we say is, this is in general incredibly tough to know in a dynamical context, but I claim we know it at equilibrium, at the statistical equilibrium.
Right. So by putting the equilibrium value into the equation, you
No, we
make
don't put it into the equation. We say we set this to 0 at equilibrium.
Right.
We set it to 0 at equilibrium, and then say there must be, forget this additional noise, there must be, so what you infer at statistical equilibrium is these third moments, which are hard to compute, are calculated at equilibrium in terms of two things you know. You know the linear operator at the mean state, climatological mean state, and you have a very good idea of the variances at the mean state. This is the unperturbed climate. This is calibration. So you know this implicitly because you know this and this. Now take this implicit guy and say, aha, to cope with these exploding eigenvalues, we need obviously some coherent dissipation in the system. So let's replace this complicated cubic term by something much simpler. That's our idea.
So that's the approximation, right?
That's the approximation.
Right. So when you showed the results for with Monte Carlo compared with this approximated
With this approximation.
equation, but with Monte Carlo, you could actually check the approximation as to how good this term captures the Q.
We have done that.
Okay.
But why should we? Our results are so compelling. Why should we bother? But we did. So we computed by Monte Carlo what the third moments were everywhere. We did this horrendous calculation because it's only a 40-mode system.
Yeah.
And the results are very revealing for why the method works. And it's in one of the follow-up papers we had. So let me then just finish the story because you asked. So then we take this known positive definite matrix and simply decompose it. The damping should be a negative flux contribution from this term. It's a symmetric matrix. Take the negative part. Write it as the contribution as if it would be a damping. You can then invert this, and show that if this is negative definite, this is positive definite, this must have negative real eigenvalues. So it's a damping term, whatever it is. So we compute it at equilibrium. And then to get the positive part at equilibrium in our model, the trace overall has to stay 0, so we pick this ratio to guarantee it. That's energy conservation. And that's the balance. Then we do a dynamical version of this by changing n adaptively according to the ratio of how much square root of energy is in the system to what it is at equilibrium. And this is simply dimensionally correct because this will scale like u squared and this scales like u. And that's cubic. Respects the same scaling. And then we do that and then out pops this algorithm. And by the way, you can use these kinds of algorithms for incredibly rapid data assimilation too. We haven't done that. But, so does that help you, Amit? Okay.
I'll have one question. Related to your first part, that the cloud, your multi-scale cloud model. So so you have different conditions to change from one cloud type to another type, or from clear sky to different cloud type.
And they depend on the large-scale state you're in.
Large-scale state here. So my question is, do your large-scale state, that is those are thresholds, do they depend on the region or and the situation?
On the what?
Like those thresholds, like that you change from one cloud type to another, or the large-scale, under what condition you change from one cloud type to the next cloud type?
Well, what we do is we have a Gillespie algorithm. It's a very cheap numerical algorithm for computing Monte Carlo. So for each grid point, we have a very cheap, if we have n states, it's essentially like a birth-death algorithm. We then randomly, we take our state and take our large-scale state that's changed and ask how much will our clouds change statistically. So we run a Gillespie algorithm that's very cheap for a short number of time steps and recompute our cloud fractions, then feed that into the large-scale model, then let the large-scale model do its thing, and then readjust.
So I'm asking that this algorithm, does it depend on the region itself? For example, you may have orography, or you may have plain large-scale.
So right now we have no orography.
Okay.
But it could. So these are all one reason I'm giving this lecture is it could involve orography. You could get built-in precipitation, but we have actually active orography here. So Bulem wants to say something.
Yeah.
I just want to answer the question.
Sure, go ahead.
So the time scales are,
Turnabout is fair play.
the time scales are prescribed, but the rates depend also on the large scale variables.
That's what I said.
You are mentioning topography, whether they depend on topography. So are you worried whether they depend on where you are?
Exactly. Not only
regionally and
topography.
so on?
Yeah, because even in the tropics, it can sometimes
Okay.
behave like
So-
mid-latitudes
Oh.
because of the weather systems.
We carry a
you
huge
take into
amount.
account
So
all those stuffs
The
inside.
With the
convection we are
Indonesian
talking
marine
about,
continent, you carry a
so the
huge amount.
convection we are talking about depends on the state of the atmosphere. Okay?
Okay.
It depends on the state of the atmosphere, large scale state of your GCM.
Okay, sure.
No,
So if you
the
have
CMT
topography-
depends on the shear. That's our stochastic CMT depends on the shear.
Your topography will give
I know
you
you don't.
some circulation,
Sure, sure.
large scale
So the model is
circulation. That's
combining these two, by the way.
will
That's to
feed
get
back
that-
into the
So you have
parameter.
the stochastic CMT. Mitch had a private comment for me. Mitch is too old to comment.
You know, yeah,
No, I'm kidding.
you know, one thing you haven't got yet in the stochastic is a dependence on the dynamic state of the environment, the shear, for example.
That's not a question actually, because
There's meant to be a question.
But
it's a framework.
excuse me, I'm the speaker. I'm going to answer that. I'm going to answer that because it's not relevant to our work, but it's relevant to Sam Steckman's lecture and Sam Steckman's in my work. So Sam, by the end of his talk, he gave all these dynamical scenarios for how CMT exchanges energy between the large scales and smaller scales. And by the end, he ended with a stochastic model for how the small scales would influence the large scales through CMT. And that stochastic model, you betcha, depended on mid-level and low-level shear. Absolutely, on whether you get active CMT or not. Yeah, so what you can do is take, and in fact, with Yevgeny Frankel, my postdoc at Quran Institute, and Bulem and I share research with him, he's now running a combined model where we're running the stochastic multi-cloud heating type model combined with a stochastic CMT model. And that's really the model that'll have all the ingredients you're hoping for, actually. So, sorry.
The self-similarity.
Okay, so you keep asking. Good.
Self-similarity at mesoscale or synoptic scale is the prerequisite for this kind of.
No, it's just the only prerequisite is what nature tells you, that you typically have bubbling convection except when it's organized. And when it's organized, it's going to be, as all observations show on every scale for MCSs, it's going to be congestus deep stratiform. So this is just a way to, under some conditions, get bubbling convection and other conditions to get organization when it should happen.
I mean, the logical flow from shallow to deep to stratiform, you mean that it should be observed at all scales?
No, it's just our GCM scales, as Mitch said very nicely in his talk, are already not going to do the mesoscale convective systems. So the goal is to do the mesoscale convective systems by this kind of idea. A cartoon for them by a stochastic model that's very cheap.
This transition probability of these various type of clouds.
I'm sorry?
The transition probability of these various types of clouds which you have discussed. So that basically that every instance it varies and every space it changes in your model calculation. They are not same.
No, right now we're doing the order zero problem. So we get such encouraging results. The spatial exchanges are done through the large-scale model. So to each large-scale grid point, we have attached a constellation of these things we solve very cheaply. And then the large-scale model grid step communicates the wave to the next step. As you saw in that convectively coupled wave, we built up an incredible multi-scale convectively coupled wave from doing that. That's all we needed to do. There are real issues. of how, when you change your grids, should you change the model, and we address those in the context of the simple models in our 2012 paper, and it's just what you'd think. If you have 1/4 coarser, twice as coarse, 4 times as coarse a resolution, use four times as many clouds. That was the best result we had. But there could be much more research, especially when you start adding stochastic CMT to how to make these things grid dependent. Here's where the mean field theory is a very good guideline. Since you can make an analytical mean field theory and get a deterministic closure, the grid dependence is very easy to untrack there. And you can check it in that limit. Yeah. I'm working too hard.
So,
this is a long day for me.
like in the beginning of your lecture, you had mentioned about the model with the deterministic behavior tending to showing stochastic behavior.
Yes, this is what happens all of the time in systems with large dimensions and large number of positive Lyapunov exponents. Coarse-grained variables that acquire stochastic behavior even though it's a deterministic system.
So that puzzles me. By definition, they are worlds apart, right? By their behavior. What is stochastic is not deterministic.
No.
How do you define this?
Stochastic means strongly mixing, rapid decay of correlations, short-term memory. And so I'll tell you, there's a very nice paper I have with Ilya Timofeyev. It's a toy model paper. It's in Physica D. I think it's from 2004. It's called Deterministic and Intrinsic Stochastic Chaotic Behavior in Dynamical Systems. And we exactly address all of these things.
Okay,
something like that. And I have a simple model that's not Lorentz's model where we address all of these things. You can take the Burgers equation, the one-dimensional Burgers equation. I'm sure you know what that is. Most of our audience knows what that is. Throw away the viscosity and write the world's worst numerical method for shock waves, which is the Fourier-Galerkin truncation. So this is a paper with Ilya Timofeyev from 2000 in Proceedings of the National Academy. That model conserves energy, and it's a fantastic model for low-frequency variability. Let me tell you why, and different from Lorentz's model. Since it conserves energy, the large scales want to create small scales from shock mechanisms, as in Burgers' equation. But it's energy conserving, so they have to stochastically backscatter energy to the large scales. So that's an example where you can start with the academic example of a sine initial data that always makes a breaking wave. You run this simulation for a long time and you get completely irregular, chaotic, strongly mixing stochastic dynamics in the large scales. So you can read it in a
So by irregular, you mean stochastic?
Meaning it can be extremely well described by a stochastic process. And so I have many papers on this. So here's I think, your problem. You're used to thinking of Lorentz system or some baby system. It's a different world when you have high dimensions and high unstable, high number of dimensions of unstable degrees. So you can acquire effective stochasticity in a deterministic system very strongly. I gave you examples throughout the lecture. My last two examples, the MMT model is a beautiful example, and the L96 model is a beautiful example of that. No stochastics there, but the behavior.
Sure.
Thanks for the